Welcome to Academic Paper Cuts, the podcast where we sit down with academic researchers and get them to break down their papers for us so anyone can understand it.
This week, we interviewed Dean Sacoransky. Dean completed his master's and undergrad in computer engineering at Queen's University. He wrote his academic paper on localizing autonomous vehicles in bad weather conditions using roadside reflectors.
We talk about a lot of things, like how robots perceive, because he used those a lot, some of the machine learning algorithms he used, and also the radar machines he used and how all that works. A lot of things on the hardware side and the software side that we break down.
Yeah, and we also just talk about the highs and lows of writing a paper like this. That's very complex. That involves a lot of technical skills. Dean's also an old friend of ours, so we've known him for many years. He's a very smart guy, and it was great to interview him. And we think that you guys will really enjoy the interview.
Welcome to Academic Paper Cuts, Dean Sacoransky. Dean is currently a generative AI engineer at IBM. In his past, he got his undergraduate and master's of computer engineering degree at Queen's University. And he actually did the work we're going to talk about today at Queen's University in his master's of computer engineering. Anything I missed there, or else I'm good?
That's perfect.
Welcome, Dean. Thank you for joining us.
It's an honor to be on the big pod, boys.
We're very happy to have you. Dean also is, beyond his prestigious academic accolades, he's also a very close friend of ours. So we are very happy to have him on the pod with us today. First exercise, I think, should we kick it off? The first exercise we like to have our guests do is explain this paper to someone like a kid in high school, or maybe just someone you're passing by on the street says, "Oh, what are you up to?" And you're like, "I'm writing a paper." And they're like, "Oh, and what?" You have like 20 seconds. You don't really feel like carrying on the conversation. Just high level. What is this paper?
So from a very high level, this paper is about how can you localize a vehicle in extreme weather conditions. So let's say there's a lot of fog, a lot of snow on the road. Typically, the driver looks at the painted lane lines, which are yellow, to determine whether they're in the lane or not. Let's say there's a lot of snow. The lanes are completely covered and you're drifting in and out of the lanes. You have no idea where you are. So the idea of this research is to solve that problem for autonomous vehicles, so they know their position on the road.
Very nice. Awesome.
That, like those words I think you use, like come up a lot in the paper, like localization, autonomous vehicle. Like I think the first thing we want to do after that like explanation is like dive into the title. Just like what are the parts of that? And like, what do those things mean? So the title of the paper is Radar-Based Autonomous Vehicle Localization Using Reflective Roadside Landmarks. So maybe the first thing there is like jumping into like radar, or in general, like what that would mean. Okay,
so as human drivers, you use your eyes to perceive the road. So that's like your biological sensor. In like this future world of autonomous vehicles, we have like digital sensors on the cars to perceive the world.
Maybe before you jump into that, just saying like what autonomous vehicles means.
Okay. Just a self-driving car. So a car with no human steering the wheel and pushing down on the gas pedal. So self-driving car, where your sensor that perceives the world is a radar sensor. So there's many different sensors, and we'll go into that later, but the sensor I chose was a radar sensor.
Okay, so we got, let's check off words in the title so that, we check them off one by one. We got radar based. So those are the eyes of the vehicle, autonomous vehicle, self-driving car. So radar-based autonomous vehicle localization. Now, so localization you kind of described as sort of knowing where you are.
Right. So, identifying your location in some like reference frame or map. An example would be when you pull out your phone and check your GPS on the maps. That's your global localization, or like in the world reference. Maybe if you're playing hockey though, and you look at the red line, the blue line, you can localize yourself to be in the offensive zone or the neutral zone, or you could localize yourself with respect to Bathurst Street. So there's two types of localization: in a global sense, where you're using GPS and trying to identify your position on planet Earth, or more relative localization. So,
Okay.
yeah.
That's great. And then the last part is the reflective roadside landmarks. So
Right.
talk us through that a little bit. What is that? What does it look like? Do we have those in existence? I'm picturing like, the construction workers, the jackets they wear and they like reflect them. Is that the right idea?
Yeah. So, like what we currently use to localize ourselves on a highway or any road is the painted lane lines, which are very visible to the human eye in some conditions. The conditions where it's clear out, there's no snow or ice on the road. We could use other landmarks to help identify our location on the road. We're using these metallic cubes, so they're reflective, like a construction person's outfit, but they're like these silver cubes.
And reflected intentionally so that they are more visible when light hits them in a low visibility environment, like if it's snowing, or is that not what?
So these reflective landmarks are specifically extremely visible to radar sensors.
Okay.
So the way like the painted lane lines are visible to the human eye or a camera in the visual spectrum, these reflective landmarks or cubes are visible to radar sensors. Because here we're not using human eye to perceive the road, we're using radar. Yeah. So we want to replace the current infrastructure with something that like matches well with the sensor, yeah.
And I think Aaron and I were talking about this. This would be a good segue into why radar? What is radar? I've heard you talk about the sensors, radar, LiDAR. Talk us through that. So why radar, first of all?
Okay, good question. So when I started doing the research, autonomous driving or like self-driving hype was pretty big. This is like started in third year.
So
2021?
Yeah. Or no, 2020, I think.
Okay.
I don't know, sometime around then. There's a lot of debate between which sensors to put on an autonomous vehicle because it's all like research. There's some companies that are like really trying to do it, but there's still debate. It's constantly changing, like which sensors to use. And there's different reasons why you would choose one over the other or combine multiple. Some reasons would be cost, for example.
What are like all the different like possible sensors that you could use?
So if we're talking about this type of, there's different types of sensors. I'll get into that. There's like sensors that perceive the outer world, which is called an exteroceptive sensor. And that would be camera, LiDAR, or radar. And then there's proprioceptive sensors, which measure qualities of the car's motion itself. So how fast the car is moving. So it's like either your inertial measurement unit, IMU, could be a GPS, could be wheel encoders, which measure like the speed of the wheels.
Okay.
There's also from the other field, the exteroceptive viewing the outer world, there's ultrasonics too. But so the main three are camera, radar, and LiDAR. So why pick radar? There's several pros and cons to each sensor. From a research perspective, you also have to consider like who's doing the most research in which areas. And you don't really want to pursue an area that's oversaturated.
Okay.
If everyone's working on cameras and you want to publish a paper and like have like a distinguished research paper, you want to go against the grain.
Yeah. For some fame.
So that's what we did. And our professor also had an inkling that radar, he was on the way up. It's like he was investing in the stock of radar. And
is he allowed to do that? Like,
sure enough,
influence his grad students' research based off his personal investments.
It was great insight. Like he thought, radar's next. Like there's a lot of improvements to the sensors right now. Like based on new hardware, AI, all this stuff. We want to pick radar because here are the advantages. It's very cheap. And that's
how much compared to like how much is a radar versus a LiDAR?
So it obviously depends which type of sensor you're using. Before me, the student had a Texas Instrument like TI radar. It was like maybe $450. Mine was 4,500.
Jeez.
Certain LiDAR sensors could be like 20, 30,000, which is very expensive. But like as we progress through time, the price is lowering. So a sensor my professor bought maybe 2015 could have been like 25,000. Maybe today it's 5. But if you're looking at like the state-of-the-art LiDAR, state-of-the-art radar, like, and camera, so radar is very cheap and camera is very cheap.
Is radar cheap just because they've been using it forever, like since many wars ago? Like,
I don't know. I'm not sure. Maybe. So that's one advantage is cost, because like any company that's building an autonomous vehicle, the number one consideration is cost. They're trying to make money. And then there's like there's the edge cases in autonomous driving. So by the time I joined, like basic perception tasks, like how to perceive the world with sensors, much of it had been like solved to some degree. But like, so let's say using a camera to identify the lane on a road had been solved with something called LaneNet. It's using AI. They're training a neural network to identify the lane markers. But in extreme weather conditions, when you can't see the lane lines anymore, how can that be done? So we wanted to focus on this edge case of poor weather. And radar is specifically valuable because it can perceive the environment regardless of weather conditions.
Because it uses
radio waves. So whether there's a lot of snow, a lot of ice, a lot of fog, or it's a clear day, the data you get from the radar sensor, your image of the world, will remain the same.
Interesting. And did you test that out when you were when you were writing this? Did you? I guess when you were testing it out, it was in good
indoors. So there's many reasons why we test it indoors, which hopefully we'll get to. At some points, I did bring the radar outside, but like there's risk of damage to the equipment, which is like practical things about robotics research, which are so different from like AI, which is pure software. Now we have like, there's rules of like where you can bring robots.
Really?
Like you can't just drive this like little car on the road per se, and then also damage to equipment is another factor. But there are some researchers who, like at big university projects, where they use this exact sensor. I purchased this one for a reason, because it was widely used in industry, in research and industry. And like other researchers had confirmed that the perception is robust to all weather conditions. It's like a known fact.
Okay.
So there's no reason to rewrite the wheel and prove it again. Like we know that.
Gotcha. Okay. That makes a lot of sense.
And so one other point, like this radar sensor, it's used by like all the big companies, big.
$4,500, eh? So that's a lot of, and just to give the people some insight into the sort of paper writing process, none of that money comes out of your pocket, right?
No. So there's research is funded. You can't just get a research job in grad school like nothing. Like the professor wants good students, because they pay the students. So, and there's a lot of like equipment. They need to get grants for equipment, and like between the robot, the sensor, and like a lot of the other equipment, which I'll talk about in the lab, very expensive.
Very expensive. Like, so it's an investment.
Yeah.
And what would you say is the return on the investment that they're looking for? Is it making a name for themselves? They're not obviously looking to sell it or patent it.
Right. So like, I think the metrics profs are evaluated on might have to do with like number of publications or like to which venues.
Okay.
So they want to be published like big conferences and journals.
Nature or something like that.
And what else? Also, like, they want to do great work and like be recognized, have a lot of citations. Some of them do want patents, or to like push out a product, which my prof did.
Oh, so they want patents. I
mean, depending on.
And then they sell it, and do you own it, or does the prof own it?
There's like a whole legal process involved with that, which I don't know much about, but like my prof did sell his IP to someone who started a really successful company out of Queens.
Cool.
On similar topics, but
all right,
off topic.
So maybe it would be a good time to get into sort of the process in which how does this work? What is the software and robotics and hardware that are all working together? Maybe we should break that down. I know we wanted to talk a lot about DBCM.
Yeah, I think one thing even before getting into the like AI side of it is like, I think we've heard the word radar a lot, but like what actually, like how does radar work? Like how does it work? Like I know you talk about radio waves, like what's a radio wave? Like what are those things?
Great question. So
taking me back.
I remember like one of my first research meetings, my prof suggested let's do like this project with radar. And the first thing I did after the meeting was go and Google what.
And I think radar thing like a Gotkin for like when they measure the pictures,
tag and stuff.
Yeah, I had absolutely no idea what it meant, what it measured, like what information it was giving back, its capabilities, pros and cons. Had to learn all of that. So we just took a sensor and used it. So we didn't have to like build a sensor. That would be more like material scientists and physicists. But I'm like familiar on the basics of how a radar works. So it like sends out a radio wave into the environment.
What is that? Like what's a radio wave?
Like some signal. And it can like bounce off certain objects. And if it bounces off an object and then it returns back to the radar. So there's like receiver and transmitter antennas. So, and then based on like the time it takes to get back, based on the time it takes for the signal to get back to the radar, it can determine how far away certain objects are. So what it's measuring is the position of objects in space and their velocity. So in two dimensions. So it can determine how far away an object is like laterally and longitudinally and the velocity in those directions. So no elevation. That was the sensor I'm working with. And there's one other thing it measures, which is like a measurement of power kind of, or intensity. So, and this is called radar cross section. So like a huge object versus a very small one will have different radar cross sections. And these reflectors specifically have like very similar radar cross sections. We're expecting a certain value.
And is that the expectation and what plays into your ability to know where you are as opposed to the reflectors as opposed to, say, a tree?
Right, exactly. So what I was saying before is you use a sensor to perceive the environment, and then like we need to formalize how we can use this information from the radar to understand our location. And I think it would be like an interesting thought experiment to go through. It's like when you're walking down the street and you want to like localize or identify your location,
like where you're
even when you're driving, like what information is important to you?
What from what I see,
like really basic,
where the other cars are and where the lanes are. That's basically how I drive.
So you want to know the position.
Yeah, I mean the lights determine if I go past. I thought maybe more if I'm on the right path or not.
So you want to know the range of objects in space, or like relative position, how far away things are. You want to know how fast they're moving. Maybe they're not moving at all. You also want to know the color and texture and pattern of things.
That allows me to identify what I'm looking at.
We take that for granted because we have eyes and like we see colors and patterns, so we know the difference between a car and a tree. But some of these sensors do not. So the first task in localization or perception is detecting objects.
Okay.
So in this research, we had to think about, okay, what objects do we want to detect?
And this is where I guess it's the reflective.
Right. So, and this is like how I went through research. First, it's like, okay, to localize like what objects am I trying to detect. And the way I formalize the problem is it's like a binary classification of objects.
Yeah.
Either a reflector or a non-reflector.
Okay. Doesn't matter what the non-reflector is. Sorry, go ahead, Aaron.
I was just thinking, like, what would a non-reflector be? Like, what's an example of something that would show up on radar for that?
Any object. It could be a table. It could be
A car.
a car. It could be a human. It could.
I have a question for you. I think we asked this to Dustin a similar question, which was, what is when you get these radar results, what does it look like? What information? Is it a chart? Is it numbers? Is it a unit? What
Good question. So yeah, and like another great thought experiment is like, what is the data you're looking at?
Exactly. That's what we're trying to.
So the radar as a whole gave me 5 decimal numbers, or like a float point, maybe 32 or float point 16. And what that means to some viewers is just a number with a decimal, like 1.5556.
Yes, that's a float point.
Yeah, so that's a float point number, and it gave you 5 of those.
And that's it.
That's it.
That's all it can
So each reading is 5 numbers.
It's almost no information. It's insane. Gives you the position in space of detected objects in X and Y, or like laterally and longitudinally.
How far it is from the radar?
Yep.
Okay.
So that, and we'll call that range. So that's 2 floating point numbers. Then velocities in both those directions.
Okay.
2 more floating point
Which
numbers.
is speed.
And then radar cross section.
Which is the power you're
Yeah.
talking about.
So that's,
Which is the size of the object?
it's like a measurement of not only size, but also reflectivity. So like silver material will have a different, So that
So
also
it has to do with the way, like, not to get too technical, but in the electromagnetic world, how well it's bouncing off the signals.
right.
And so is that those, I guess, variables, are those for every single detected
Every
object?
reading?
Exactly.
So it could be infinite detected objects.
How fast is it reading?
It's limited. First of all, it's limited in how many objects it can detect in space. And as an engineer or a researcher, I chose how many objects I wanted detected in space. And then how fast. The radar maybe it's like 13 hertz, so 13 measurements a second, I think.
Okay. For the listeners, a hertz, the unit of a hertz is just per second.
Yeah.
So 13 hertz means 13 per second.
I think one thing, like, about talking about, like, you talk about their speed, velocity, and cross-section, like, to me, not speed, velocity, distance, velocity, cross-section, to me, distance seems pretty intuitive. Like, you bounce the light signal radio wave off a wall, comes back, the time is going to be how far. How does it figure out speed or velocity?
So that has to do with Doppler, which you could probably explain better than me.
I did a little bit of physics, that's why you said that.
Yeah. So it's just maybe we don't want to get too technical. It's an advanced sort of physics signal processing way of determining speed.
It shifts from being a certain type of radio wave to a different type, and based on the type of radio wave, then you can know how the speed is from that.
Yeah. The Doppler effect is when an ambulance drives by you and it goes, it likes the frequency, the pitch at which it sounds, it changes as it passes you.
But so I should mention though, so this radar gave us these 5 numbers for each object we detect in space, but that isn't the raw radar information.
That has been processed?
So there's onboard processing, and there's a reason why I bought this sensor. That's one of the reasons. So you could buy a sensor that actually gives you the radio wave.
Oh.
And you
meaning like what? Like a wave?
Like polar coordinates.
Okay.
And then you need to do like fast Fourier transforms.
Oh, that's, yeah.
And another algorithm called CFAR to convert that information into what you want, which is range, speed, and power. So I bought a sensor where they did it on board, because I'm not rewriting the wheel here. That would take me 2 years in itself.
No reinvention of the wheel. Yeah. Okay.
Yeah.
That's a whole paper in itself.
Yeah. So, okay, this radar sensor gives us these properties, which are valuable when you're trying to like analyze the world. But there's other missing information that is also really valuable, like color and texture. So when we're looking at like the data in the computer, all it is just like a dot or like a point for each detection in space and how far away it is. We call that a point cloud. So it's like a cloud of dots.
And is each dot represents the distance from the radar?
Yeah, so it'll give you the cloud, or the point represents its position in space away from you. So the one that's like 10 meters away will be...
Yeah, but where's the velocity on that point cloud and the power?
So you can't, like, you could just have a
higher dimension.
If you're visualizing it, yeah, you can't visualize the velocity. Maybe there could be like an arrow. Or
yeah, okay.
But yeah, so you're really just looking at dots in space. You have no idea what's what. Like, what's a reflector? What's a tree? You're not in the visual spectrum where you can...
You got to readjust the way you're thinking of it, right?
Exactly.
So did you do that at all to get the texture and things, or you just had to figure it out based on that information?
I had to figure what out?
Like, to be able to like understand what object was a reflector versus a non-reflector. Was it purely based on that information? How did you figure out a way to bring in that color and texture?
Only radar.
Okay.
So that's it.
So ideally, there would be a sensor in the world where you have color and texture, like a camera.
But you need light for that, no?
Yeah, but
and
maybe
radar.
There's going to be some super sensor invented where they can have that.
Where they'd have radar and light combination.
So I want to explain a few new sensors. But first, let's talk about the different types.
Okay.
So camera, why is it great? It looks like your perception of the world is similar to ours. Like we look
at an iPhone camera. It's an iPhone. It's literally a camera.
It's a camera.
All right, not to get too...
So you can see the color of things, very rich information, but you don't know the distance.
Why?
Because
it's just too extreme.
Exactly. There are certain
you can infer the distance, but it's not actually part of the raw measurements that it's
exactly.
perceiving.
And there's certain things called like stereo vision setups where you can do that, but like for the sake of using a camera in its raw form right now, you don't have a distance measurement or speed of objects. So like this is why like engineers will combine multiple different sensors.
Okay.
So that's a benefit of camera. A benefit of LiDAR is it's extremely dense information. So once again, you have these points in space, the same as radar, but it's like a very complete image of the world. And it's 3D, whereas radar is 2D.
Mm-hmm.
So you have a lot of information. You have the distance and, just the distance in 3 dimensions, no speed.
This is for LiDAR.
Yeah. So radar, you have the distance in 2 dimensions and speed. LiDAR, you just have distance in 3 dimensions.
And LiDAR uses not radio waves like radar, but light waves?
Yeah.
Not to get too technical, but don't cameras use light waves as well?
I don't know. I can't really talk on this stuff because I was like focused
You're
on
a radar guy. Okay. We're the radar guy. Okay.
So now there's 2 new sensors on the market. Doppler LiDAR,
okay,
which measures 3D space, very rich, complete information plus speed.
Okay, so how expensive is one of them?
Probably really expensive,
like 50 to 100 grand.
I don't know. I'm not sure.
When did they come out?
They were talking about it when I was just leaving.
Okay.
Oh wow.
Who makes them? Like who owns the Doppler? Like is that like Texas Instruments? Is like did Tesla make it for their cars?
Velodyne is a big LiDAR company. I don't know. That was the big one.
Yeah. Okay.
Velodyne.
Okay, so sorry to interrupt. Doppler LiDAR was the first one.
So that kind of solves the issue of LiDAR not detecting speed of objects. And then there's 4D radar, which measures space in 3D and obviously also a speed. So they're pretty much very similar. And it's really important that you want to have like 3D image of space and detect the speed of things. Because like we kind of went off on a tangent, but to like bring us back to where we originally were, when you're walking on the road or driving and you want to understand the environment, it's important that you have like a dense representation of what's in the world. You know the distance to those things, and you know their speed.
Aha, interesting. Okay. So I think we've done a lot on the radar. I think I've learned more about radar right now than I think I've ever learned in my entire life. Now let's move on. So you have the 5 numbers, right?
Yeah.
You have sort of an understanding. You're getting a lot of information of things in the environment. You're getting their X and Y coordinates and their speed in those directions and their power. How do you turn that into, okay, I know where I am on the road? So it seems like we've done a lot of the hardware. Now we're moving more into the software portion of your paper.
So one of the key strategies in determining your position in space with a robot is by detecting static objects in space. Whether that's like, you can use like detecting trees and buildings to have a better estimation of the way you're moving because you know they're static.
Yes, you know they're still. Whereas like other cars would be harder because they're moving and you can't pinpoint.
So you want to detect things that are not moving in the environment, and ideally you want to know their position relative to the road. So if we can detect a static roadside landmark, or like these cubes that are on the side of the road, then we know we should be maybe like half a meter to the left of it, and then we're in the middle of the lane.
Because we know where those roadside landmarks are relative to the lanes.
Exactly.
So you try them. Okay.
So the idea is we implement this infrastructure, we put it in space with a purpose so that we can detect it and it will help us navigate the road. And we're looking for these static objects and they have like a very particular configuration in space. So they're going to be lined up. We know how far apart we're spreading them out. Maybe we choose to spread them out by 1 meter, which is valuable information.
Okay. Okay. I see where you're going. And so how would you configure? How'd you configure it?
We got to look at the paper. It could have been 1 meter apart. I honestly
you don't remember. I think was this a big conversation you guys had, or not really?
Not a big conversation.
It just needs to be known.
Yeah. So and like the great thing, about engineering is like you design the problem and you like make choices that make it easier to solve. So we're gonna spread them out at known spacings. You want to identify or detect these reflectors. So there's so many things in space, and like the question is, how do you do that? Is that your question? Yeah.
Well, how from the radar data did you end up knowing that you were driving right? So you just have numbers,
right?
And those numbers indicate location, right? And we know that those numbers indicate location, and from there we can triangulate from the relative location where you are on the road. Mm-hmm. But how do those numbers become an understanding?
Yeah. So that was I spent the first large portion of my research trying to solve that problem, and there's different approaches you can use. So given your data, like how do you understand what is what? Mm-hmm. And some would use AI maybe.
Buzzword. No, I'm kidding.
To be more specific, actually, there's like that's meaningless what I just said.
I know, well, because I'm just showing because he works in generative AI. But he's a real AI engineer. So what did you use? I'm sure you employed some version of AI.
Yeah, so it helped that I had like a good understanding at the time of different techniques that could be used, because ultimately it's a pattern recognition problem. So you're just looking at objects in space that are configured in a certain pattern, and you want to identify that pattern.
And the pattern being what are the reflectors and what is nonsense?
Exactly.
That's just the radar's picking up at maybe a tree or whatever noise.
And the reflectors form a line that are evenly spaced.
Or a
curve.
So it'd be really hard if birds were flying by in a perfect
right, exactly. So you're pretty much
mimicking the road.
Yeah.
Exactly. You're trying to find objects in space that form this linear pattern or like a curve pattern.
And to be honest, that doesn't sound that crazy when you know that they're going to be spaced apart. I know it probably is. So what are the challenges in doing that?
So first thing I did was like, okay, can we use some machine learning technique? The problem is, one, you have so little information.
Yeah.
As I explained, and we're at that mutual understanding. And to do machine learning, you need a big data set.
Yeah.
So, and you need a data set of certain objects. So I would need to somehow stumble upon a data set of radar measurements of retro-reflectors.
Which is crazy.
Pretty niche.
There are radar data sets with this exact sensor I have, and that's why I bought it. Because I was like, okay, if I want to use machine learning, I need a radar that has massive pre-existing data sets. So I bought this.
And when we talked to Dustin, our first member, about the data sets he used a massive data set of EEG readings, right?
EEG and a mode.
Yeah. And he also they had their own proprietary data set that they created at Queens.
Yes.
So you didn't want to create your own data set. It was too crazy.
Building a data set with sensors is extremely, extremely challenging.
Like you physically just have to do the thing.
So time consuming. Like it's not possible for me individually to build a radar data set.
Too much manual work.
Yeah.
Like our private companies that are utilizing radars and building off machine learning like Tesla, are they building their own data sets and labeling and creating it all from scratch? So
there's couple big data sets coming out of Oxford and coming out of, there's a new scenes, it's called the new scenes data set, which contain this radar, but they have like real vehicles and they strap radars on them that abide by like certain safety protocols, and they drive them out on main roads for like, I don't know, thousands of hours, like tens of thousands. I don't even know how long, but it's like millions upon millions of data points.
Do they like
might be like 10 million radar scans? Yeah. So I have absolutely no interest doing anything like that.
So you wanted to work with, you didn't want to use machine learning because you didn't have the existing data set with road reflectors.
Right. So I didn't want to use supervised machine learning.
Yeah.
So there's different types of machine learning. What we're talking about, where you have a data set.
We kind of went over this with Dustin. Maybe we should do a quick recap. Tell us about the 3 different types of machine learning models.
So there's many.
But is it classically like supervised, unsupervised, and that partial?
We could do I could talk about supervised, unsupervised, and I guess self.
Self was the third.
So supervised is like where you have pictures of cats and dogs, let's say.
That's exactly.
You're all the same.
Actually have an Excel sheet with like a bunch of cats and dogs, and next to the cat you write cat.
Yeah.
Okay.
Next to the dog you write dog. So you like clearly specify the answer to the problem, and the problem is what is in the image.
Sounds like a fun job, honestly.
Unsupervised learning is where you only have the problem and not the answer. So you would just have pictures of cats and dogs, and you don't tell it what's what, and you try and find a pattern. Maybe you'll find that all of the cats form a different pattern in space, different pixels, rather than the dogs. So you just find patterns through the raw information.
Could be like.
And how do supervise? So supervised, we know when we're right or wrong, because we know if it's a cat or if it's a dog because it's been labeled. For unsupervised, how do they know if the pattern that they're inferring from whatever data they're using is correct or incorrect?
You'll have to do some evaluation.
And grade it.
You need to establish a ground truth. You would actually have.
Yeah, ground truth gets thrown around a lot.
Yeah, that's the true. That's the truth, the true value. So when you're looking at pictures of cats and dogs, someone needs to define the ground truth. To us, it's very obvious what the cat is and what the dog is, but there might be a cat that looks a lot like a dog.
It's like a happy cat.
So the data set creator will have to tell us what it is.
Okay.
And this becomes very hard in certain things, like stuff I'm working on now, evaluation is really hard. But for the sake of image recognition, it's pretty basic. And what we're doing here is object recognition, but with reflectors. I'm not, kind of got off topic. I talked about unsupervised, supervised.
So supervised is cats and dogs that are labeled. Unsupervised when you have to find the pattern yourself because we don't have a label.
And then one other type is self-supervised, where you're actually like, you come to this crazy realization that like the labels were already there for you. And it's like, to me, it's like the most insane thing in all of AI was this, when I like discovered this. So like if you're reading like a book and your task is to predict the next word in a sentence, so you want to predict it, and maybe you're using some AI. How do you find the ground truth? Just by looking at the next word. So what you can do is kind of like block it out. It's called masking. You pretty much put your finger over the word.
Yeah. And you try to guess it.
Try and guess it. And then after you guess it, you take your finger off and look at the answer. So
and
what we've done is, if you then iterate over every single word on all of the internet, you then have labeled, or you've supervised like trillions of data points, which pretty much solve the issue of like data set creation. So it was the most insane thing.
And that's really used in like large language models, which is more like the natural language type of AI rather than what you are doing. Or
so like that's used also in vision now, where like you block out certain pixels of images and patches. And like some people are using these like neural networks for radar. I saw at the conference I was at, like transformer networks.
Oh yeah, we didn't talk about the conference. We'll talk about
it. So there's no reason why I would go down that path, because in order to make good use of those neural networks, you need massive amounts of data.
Yeah.
To like get your return on investment, and we have so little data.
Okay.
So the choice obviously is unsupervised learning.
Okay.
It's a no-brainer.
Yeah. So tell us. So unsupervised learning is you sort of have to extract a pattern on your own and then establish a ground truth and check your answers, evaluate your answers based on that.
So we have the radar. It's giving us detections of objects in space, and we're just going to try and find a pattern. Like, okay, we see a cluster of objects here. We see a cluster of objects there. But there's different types of clustering algorithms. And there was one that was specifically perfect for my use.
And so clustering algorithms is what? I remember learning about it in computer engineering, but for the crowd, what is it doing? What does that mean?
So like if you're at a party, and you want to like identify groups around the bar, and like a group at the couch, those are clusters.
Which one would you go?
People like at the bar. Yeah. Or like in the playground, there's certain clusters of objects. So you're actually just looking at the density of points in space.
So in your case, it would be like looking at the data points, and some are going to be a little bit on the right, some are going to be the top left, and like kind of creating a circle around them.
Right. So you're just trying to find a pattern in space.
Okay.
And certain clustering algorithms find patterns that are circular. Is that useful to me? No, because the expected pattern of these reflectors is a line, either a straight line or a curved line.
Okay.
In the example, would be for a highway going straight or a highway ramp where there's a curve.
Yeah. Okay. Was it harder for the curve than straight? Just intuitively, it feels like it would be. It was not.
No.
Okay.
Because the algorithm I chose can actually detect any weird pattern in space.
Do you just have to define it beforehand?
Define
what the pattern is going to be, or it
does it itself?
So this is DB scan, just to be clear. And so that word is all over your paper. DB scan. What is that?
So it stands for density-based spatial clustering of applications with noise.
Okay.
And it's just like a density-based clustering of objects in space. There are two parameters you choose. So let's say you pick one point of interest in space in the playground. First, you want to build like a neighborhood around them. So that's like our epsilon value, or like the size.
How big we want the groups to be.
Yeah, or how far away we want to investigate.
Okay.
So we first just investigate like in some radius around that point. And
like how many feet away from the bar are we willing to consider at the bar?
Exactly.
Okay. And how many feet away from the couch are you considering on the couch?
Exactly. So let's say...
and that's epsilon.
Yeah.
Okay.
So let's say, and it's just a radius around the point.
Okay.
So let's say like it's 1 foot away from the bar, then you're at the bar.
Yeah.
Okay. So then that guy who's a foot away from the bar, we're saying is at the bar.
Uh-huh.
So then we look at that guy and we draw 1 meter,
Oh, okay.
1 foot radius around him and say anyone 1 meter away from him is also at the bar. And then what you find is you've created a whole Congo line across the bar in a weird shape, because you're not trying to find like a circular cluster. It's density based. You just want to find a connection between one point to the other, and it can take you anywhere.
So, okay.
So
that's not...
that way?
No, it allows you to create a cluster of like a line or a curve or even like an oval or any shape. Even if the middle, let's say you create a circle, the middle doesn't have to be populated. It's just that line, just a connection.
Okay.
It's like
So you were talking about the distance. I forgot the exact word off the top of my head. I know it's in your paper. I read it. Do you know what I'm talking about?
The Mahalanobis distance?
Yeah. What is that? What that is? The what's the word?
Mahalanobis.
Mahalanobis.
So that's actually
a great word.
a completely different topic in the paper.
Okay. So pretend I didn't ask it.
Yeah, we're like long way away from that.
We're just on deep.
So we're on density based clustering.
Yeah. So
We're cool on the density.
to wrap it up, unless you guys want more detail, let me know. But based on the density of positions of objects detected in space, we can form these clusters. This algorithm was perfect for detecting lines in space, which is why I chose it. So I'm happy I stumbled upon it. Otherwise, I would have been screwed. I don't know what would happen. And yeah, so the cluster, I pretty much want to find this cluster of a line. And then that, to me, those are my reflectors.
So is this... Go ahead.
Do you like actually, like this is the unsupervised algorithm you're using.
Yeah.
So like, do you actually know how that algorithm's working, or it just does it? Like,
Well, I just explained how it's working.
but like, do you know a deeper level of how the data is being manipulated?
Well, like, what are our inputs to the algorithm?
Points.
Our points in space. So it's like it was X position, range in space and power. It's 3 numbers going in. And the output are like classifications.
Is this like, I'm sure, so when you wanted to apply this algorithm, it's publicly available. You can just go download the code and read through it and check out the math.
Use it as a black box from like sklearn library. And you could just set its inputs, and then the output would be, for each point in space, it would give you a 0 or a 1 or a 2.
And that 1 or 2 means...
The 0, 1, and 2 represent the groups. So group 0 is at the bar, group 1 is at the couch.
So is that what you were trying to do with your information, where you were trying to look for who is at the bar, meaning which are the reflectors, and who's at the couch, meaning which is just a tree or something that I don't care about?
Yeah, I wanna look at the different groups that are outputted, and based on them, try and understand whether those are the reflectors or not.
Okay, so that's sort of what the AI, quote unquote, buzzword in your paper was doing. Was that the unsupervised algorithm?
Yeah, so I honestly wouldn't even call it. I don't think it deserves that buzzword. I would,
That's not the point of buzzwords. You just throw them around however you see fit.
I guess that let's call that our detector, our way of detecting objects in space.
Okay.
It's the equivalent of you knowing what a tree is and what a car is inherently, because we're intelligent. So now we've given our radar that capability.
So now you know where,
but with some
is.
degree of accuracy and some degree of failure.
Okay.
How do you know when you're wrong?
So, in the broader localization algorithm, or when we're evaluating it?
When you're evaluating, hey, okay, I'm looking at the results. They work good,
results.
But how do I know they're good?
So, great question. So at the lab, we have something called a Vicon motion capture system.
That's always as good as the word. What did the other miss on?
Mahalanobis.
It's just like, really, that's probably the most expensive thing in the lab. I honestly couldn't even tell you. Cameras set up like all around the ceiling, like they're built in, and they are monitoring the space. and we can tag certain objects in the space for it to track. So what we want to establish the ground truth position of the reflectors in space. And this is why we worked in the lab and not outside. So we tagged each reflector, and then we had an origin point in space, and that was where the car was going to start. So then when you calculate the difference between the origin point and
car
and the reflectors,
okay.
then you know the range.
And then you know how far the car is from
And
the
we're
origin.
similarly tagging the car. So we're doing all of this, so we know exactly where the reflectors are in space, and then our algorithm also gives us a prediction of where they are in space.
Okay.
And then we can calculate the Euclidean distance error, or like the tracking error. So our prediction of where it is in space and how right or wrong we are.
Okay.
In 2 dimensions.
And Euclidean distance is just the radial distance.
Yeah, XY distance.
And question is, so the DB scan algorithm is very general, and this is like a very specific application of it in your own environment. So did you need to write any code or create any software that compared the results you got to the results of the environment? Was that part of the process?
How did in my evaluation?
Yeah,
that was one of the hardest things.
Okay.
Testing and evaluation took so much time. I needed to be able to extract all that data from the Vicon and
like map it to the
and
the radar.
compare it and have it time stamped. So I needed because
that's the most important part, right?
Yeah, we're doing it in real time. We're driving the car around in space. We need to have all the time synced up, and maybe the algorithm makes predictions at a different frequency that the Vicon measures at.
So then you got to map it up, right? Like one's every half second, one's every 3/4 of a second.
Downsample. So these are constantly, you're running into these crazy challenges, and you have no guidance, but you have to figure it out. And that's the beauty of research.
So, because it's true, no one's done it, right? You are the pioneer.
Well, there's maybe there's,
but in
people
this very specific application, it's not like I'm writing a test in physics and I know that all the graduating classes above me and all of the students who took the course last year learned the same thing, wrote the same test, etc. This is brand new.
Yep.
So now you have you're able to figure out this line, right? Mm-hmm. What do you do from there?
So First, I was doing it, and it was working really well on a stationary vehicle. I could actually identify in space. On my computer, I had it visualized. The reflectors would show up in green, all others would show up in red, and I'm seeing the green line or the green curve. Great. What happens when I then start driving the robot or the car?
Did it all fail?
It all goes to shit because there's a lot of vibration and noise. And radar sensors to begin with are extremely noisy sensors, meaning it's if you're holding up a camera and running and filming, is it going to be jumping like crazy? That's the case with radar. Suddenly everything goes to shit. It's a very hard sensor to work with.
So what'd you do?
So that's when the second or the main aspect of my research came in, which was the fusion algorithm. So it's
fusion.
So it's in order to limit the impact of this noise, we're going to take information about how the robot's moving and fuse the two. So we can measure how fast the robot's moving with wheel encoders.
Yeah.
So we have a special robot and we know how fast it's moving, but there's also some noise with respect to that. There's errors with the way the robot speed is measured, and there's errors with the way the radar measures the environment. So now what I was getting at the beginning is there's proprioceptive onboard sensors and exteroceptive visualizing the outer world. Now let's fuse the two to smoothen out our radar measurements.
So you have
that when we drive, points aren't jumping all over the world, but rather they're moving smoothly the way we expect them to.
And how does it actually make it seem that it's smooth? What's it doing?
What's going on? So my best analogy for this fusion algorithm, which
I want to hear your worst after this.
it's called a Kalman filter, and it's one of the most common algorithms in engineering. My analogy would be if you're staring at the wall, you're using your eyes to perceive how far away it is, and then you start walking towards it, you expect the wall to get closer to you as you walk towards it.
Mm-hmm.
If it doesn't change distance to you and it remains the same distance away to your eyes, you'll think that either you're going crazy or your eyesight isn't working.
Or the wall is moving backwards.
Yeah, something doesn't make sense here.
Yeah.
Because you've like a internal representation of how you're moving.
Uh-huh.
And you also have a representation of how you're perceiving the world, and you want to combine the two.
Okay.
So that is my analogy for how this works.
So what it's doing is it's not only knows that it's moving. We not only know we're walking towards the wall, but we should also see it getting bigger.
Yeah, we expect as we walk towards the wall, we expect the wall to appear closer to us with our eyes.
Uh-huh.
And as we drive towards these reflectors, we expect the radar's measurement of them to reduce in range, or we expect them to move towards us, pretty much.
Okay, so
that's what this sensor fusion is.
And so that you're saying that was the most challenging part of your paper. When you're like, okay, it's stationary, I'm good. Were you expecting that, or what?
Well, like at the time, I was like, how the hell are we going to fix this? Like, there's no way, like, it'll work. And my professors were just very confident because they're experts in the field, and they're like, no, like, just do the Kalman filter.
Is that like a dance move?
It's like they've seen it a million times, so they had faith, and I just followed. But it was very challenging.
How did you? Okay, like they tell you to do the Kalman filter. Where you go on medium.com and read about the Kalman filter? Like, how do you?
Yeah, like read papers. Literally go to the whiteboard and write out the math. Like translate math from online to on the whiteboard and adapt it to your problem setup. So you're not just like doing a generic algorithm. It has to be custom to your problem setup, which is a specific number of reflectors in space, certain data that we're measuring, which is like X and Y. It's two numbers.
Okay.
Yeah, like literally had to formalize this problem in math, which was really challenging.
A lot of math in your paper, right?
Yes. And the biggest challenge of all is the radar has missed detections and false detections. Let's say at time step 0, it measures all 10 reflectors. But then at time step 1, it only measures 5.
So now,
how do you associate points from one time step to the next?
If some are missing?
Like when you're walking down the street and you see a car, our brain knows as we move and as time progresses that it's the same car we're looking at. But these sensors don't. So the sensor itself is creating a fresh measurement every time step, maybe 13 times a second.
And so
with no context of what it saw before.
And so how is
measurement?
So is that what the Kalman's doing? Is that the Kalman?
Yeah. It's like
Kalman it's called?
Kalman. Yeah.
It's linking previous measurements with future measurements.
Yeah.
And the change in their
exactly
density and whatever.
For a recursive algorithm going from one time step to the next. Exactly.
So is it like predicting where it thinks it's going to go and then judges it?
Yeah. So there's two steps, like prediction step and update step. And those two steps use different sensors. But
cool.
I don't know if you want. Yeah.
So we've kind of got the broader picture of how the paper worked end to end. Did we miss anything? We went from the radars to the clustering to the fusion, the Kalman.
Few other points I might want to hit on is, so like when you're walking in space and you can like track an object. So there's a difference between detecting it at one time step and tracking it over time. To track it, like maybe your eyes actually get different readings at every time step, but your brain is intelligent enough to associate the same object over time steps.
Yeah.
Similarly, the sensor is measuring freshly at every time step, but the algorithm or the software is like the brain that can...
That's keeping the memory. Yeah, okay.
Yeah.
Okay, cool. You keep calling us intelligent, saying I know that I'm a cat and dog, and that I know that cars get bigger as I drive towards them.
So Yeah, I mean, there's obviously more details we could go into on like how do you associate different points, but I don't know if maybe I don't know.
I mean, we're whatever you want to talk about. We're almost at the hour point, so maybe a little bit more. If what do you really want to talk about?
How
What we
much
missed?
do we have altogether?
Whatever you want. The world is yours.
I mean, I don't think we need to go there. It's very technical.
Yeah, that's fair. So like you got all that. Like what were the results from doing that? Like how was it good? Like
Yeah, so like we had to do all this testing, which is really hard. That was like honestly maybe the biggest challenge. And we needed to pick how we were going to evaluate it. There's no like standard for how to evaluate this type of research. Like
So you have to make up your own grading scheme.
yeah, like when you're detecting objects and images, it's accuracy. How accurate were you at detecting the dog versus the cat?
Yeah.
It's not like
So what did you use?
it was tracking accuracy. So how accurate was our prediction of reflectors in space? And the result was 25 centimeters. That was like
On average,
averaged Euclidean distance tracking error over all of our experiments for lines and curves.
I think also it would be important to note for the listeners why this is so important where we already have GPS. Is it obviously because it's way more accurate? Or is there other reasons why it's made? Because like GPS can't tell me if I'm in a lane or not, right? But this could tell me if I'm in a lane.
Well, and there's certain environments where GPS doesn't work, also underground, for example. So like there's failure modes of GPS, which are different from the failure modes of radar.
Okay. And why don't you tell us a little bit, two things we want to know. We always ask is, what was just the hardest part of the paper? And at any point did you think, I'm not going to complete this? So what were the hardest parts? What was that?
Every day of my grad studies, I thought I wouldn't complete it. My mom knows that. I'm there every day. The hardest was probably the learning curve at the beginning, like having no understanding of anything I was reading, no understanding of the software frameworks, no understanding of how you get information from a sensor. How do you plug it into, are you plugging it into a computer? Like, how does this work?
Yeah.
The learning curve at the beginning of both like conceptual understanding. So reading the literature and like understanding the algorithms. So knowing which algorithms to choose in certain areas and then doing it, like actual implementation, extremely challenging. Having to learn this full new software framework called a robot operating system.
ROS, which is
like insanely difficult to learn.
Is it hard to program in? Is it not? Is it similar to any other programming languages that
it uses some Python, some C++, some like XML, Bash scripting, like CMake. There's like multi-threading. So you're running like several programs simultaneously because you're measuring from different sensors. But it gave me a really good like mathematical or like engineering perspective on how information is passed. So like it followed a certain paradigm called publisher subscriber. So everything is either publishing information or subscribing to information.
They're given or taken.
Exactly.
Okay.
Then like you could guess what's giving and what's taking. It's outputs versus inputs.
Yeah.
And that's everything. That's kind of the way I think about problems now. Everything is an output or an input or the black box.
So, okay, interesting. And I guess last thing would be, you're a generative AI engineer now at IBM. This is more on the robotics side with clustering algorithms. It's not really, is this at all related to what you do in work?
No. Like a lot of...
Did this give you credibility that helped you get your job? Or not really?
I don't even know about that. It just like, it really did, going through it really made me like more confident in my abilities to solve technical problems and just my technical ability. Like, I had to figure out like a million things along the journey. So it made it easier to figure out generative AI when I was preparing for my interviews. But I also, in parallel to doing this research, was learning about generative AI and like language models.
Was that in your coursework or just personally?
Bit of both. But Yeah, I mean, I always wanted to make use of all this stuff I learned and like actually get a job in that field. I don't know if I'll ever write a ROS program again. And there's like not that many people in the world, honestly, who know ROS.
Really?
But there's so few jobs hiring in that area. It's
Yeah, okay, fair.
the return on investment for learning robotic stuff, I'd say, is very low, because it's so hard, like extremely hard. And right now, there aren't that many jobs. That probably will change soon. Whereas in generative AI, it's all-time high.
Right now, it's like,
Yeah, like
it's all
if
the
I-
buzz, right?
One software framework to learn, it would be LangChain, and that like
That's,
the dividends are massive.
okay. And you submitted this paper to a conference, right? You were in
Yeah.
London, England.
London, England.
And what was that like?
It's crazy, coolest experience ever, still to this day, career-wise or any academic-wise.
Did you speak in front of a group of people?
Yeah.
Or did you have like a Bristol board? Like
Poster presentation, only the top like few papers in the world had PowerPoints, or like it was like famous people giving PowerPoints. But I mean,
I remember you telling me there were people from NVIDIA,
Yeah.
Google.
there were two people who had similar papers to me. One was NVIDIA. It was awesome, like using the exact same sensor.
Oh, that's awesome.
But they're part of the whole team, met them, and then one other guy. But like, it was just the coolest thing. All the companies are there. All these like great researchers.
It's awesome.
Want to go back to another conference, so maybe me and
Can you do that? Can you resubmit your paper and go to like another conference?
I can still submit work, but like I would probably have to take time off my work.
Yeah.
They're not just going to let me go unless it's like a paper
For
IBM,
yeah.
and then maybe they still wouldn't let me go. I don't know, but I hope to do more research at some point in life.
That's really cool. I think the last thing I wanted to know was just like what, like, we asked the same question at Dustin's, like, what were you physically doing for most of this paper? Like, what was happening? Like a pie chart of your time spent.
Most of my time I was on a laptop right next to the robot with the radar, and it was plugged into my computer. So I'm like getting information and I'm debugging my algorithm.
Debugging, meaning going through everything.
Meaning trying to find if there's mistakes somewhere, looking at the data.
Do you still have the hard code?
Yeah, I have all the code. It's in a repository private, like with the university, but I still have access to all the code.
So most of the time you're sitting there looking at the robot. What about like, were you in the lab most of the time, or were you just like in your room at your desk?
So most of the time I was in the lab, literally plugged into the robot and sensor, writing code or like trying to understand what I'm looking at, the information. But then I learned how to do it in simulation. So I could like collect data and like simulate everything going on.
Meaning you didn't have to be there.
Exactly. Okay. So I finished off at home. Like I wrote the last portion of my algorithm at home and tested it at home and evaluated it at home. Because I ran all the tests preemptively.
Nice.
I wish you could have done that earlier.
Yeah. But no, it was a great experience being there. And a good portion of time, I was like at the whiteboard trying to understand the math with either other researchers or my prof.
And do you want to give a special shout out to your prof?
Yeah, special shout out to Josh.
Josh, he was
shaped me.
He was also my Dean and I were in the same capstone project group. He was my prof. He definitely doesn't even remember who I am. But anything else you want to add, Aaron?
Was there anything really dramatic or anything that happened?
Yeah. Did you ever give a big fist pump? I just drained a big putt.
Yes, there were so many different. It's crazy what my
biggest fist bump. What was it?
Probably my first big fist pump was when I used DV scan. The first time I got it to work on radar and I saw the detection of a line. I was really fired up.
And did you ever almost punch a hole through your computer?
Yeah, for sure. Or when I first actually just got data from the radar, it was oh my God. Because
this is it. It's the real deal.
In order to do it, my colleague realized that we had to break open the wires and put a transistor in. And I just had the confidence in him to do it. It was insane. I never would have
in your $4,500 rate. And if you opened it up and added a transistor.
Yeah, and if it broke, I don't know, I just would have gone in a lot of trouble. Like, you were reading the documentation, and that's what they said to do, and I was just crossed my fingers.
Who was this?
Kai Wang, shout out, Kai Wang.
Was he another researcher?
He was in the same lab as me, working on cool stuff.
What was he doing?
Like robot follower stuff, like one robot behind another.
Oh wow. A lot of cool research out there. That's the goal of this podcast. We want to learn about what everyone is doing.
Cool stuff. But yeah.
Well, we really appreciate your time. This was more than enlightening. Aaron, do you have anything to add?
I think that was just really awesome. It's like cool to get in the mind of like what a robot is.
Yeah. Thank you, boys, for putting the spotlight on this, the research.
Yeah, we'll share the link in our bio for anyone who's curious to read it. And big thank you to Mr. Dean Sacoransky for joining us.
Thank you, guys.
Thanks, Dean.
All right.